quiz or exam, so you can be relaxed. Chapter 27 is about circuit theory, and most of you have learned it for in your last semester. So this is a pretty simple one. E equals I out. So that's it. And yeah, V equals I out. And loop rule, resistance rule, EMF rule. Pretty strange. Actually, it tells you about the internal resistance. So for real battery, it can be equivalent to something like the ideal source in series with internal resistance, which will be usually a small resistance, a few ohms, something like that. And actually, this will have some sort of voltage drop here, so that it will not be something like the V over R, but originally, if this one is E, or usually we write as V. Originally, here we write V equals IR, V equals IR, but here we'll write it something like V equals I times or R plus R. And so resistor in series, so we just add them together for potential difference. So the power is something like I times V, which is also very simple. So here we will have a slightly more complicated circuit. So it try to write many equations, and you will get lost, of course. Okay, let's come to here first. For parallel resistor, we take the inverse and add them together, and then we take the inverse again. Then it will be the parallel resistance. And for here, let me give you an example. So actually, we have a circuit like this, and 2 ohm, this one equals 3 ohm, this one equals 1 ohm, this V1 is 5 volt, this is 8 volt, and I try to solve it in 2 different ways, and actually that's basically what you have learned in the first semester, the first half of the semester in the circuit analysis. And so, first one for the first one for the loop KVF, Kirchhoff current, Kirchhoff voltage law. So we'll assume 2 loop current for these 2 loops. Going counterclockwise. So for this resistor,
we will have voltage drop R1, I1, and for this voltage source, it is something also like a voltage drop, so it is positive. And for R3, I1 is going counterclockwise, clockwise. I2 is also clockwise. But actually, when you see this loop, something like this. Okay. So for R1 going this way, for P1 going this way. So voltage drop, and for R3, I1 is in this direction, I2 is in that direction. So that you write R3 times I1 minus I2 equals 0. And likewise, we can write it for this loop, and actually for this one, we have I3 and I2, and this loop is in the same direction. So we have I2 minus I1, and this is not voltage drop, so this is minus V2 plus R2 I2 equals 0. And you can rewrite it into something like R1, R3, R2 plus R3 minus R3 minus R3. And I1, I2 equals minus V1, V2. Something like this. You can rearrange the term and you can get this. So finally, I1, I2 will be something like the inverse of this matrix, something like this, minus R3 squared. And then we exchange these two terms, and also give a negative side to these two. So we have R3, R3. So finally, we can substitute all the number in it. 2 plus 3 minus 3 squared. 2 plus 3, 1 plus 3, 3, multiply minus 5, minus 3, 1, 2. And this is minus 5, 8. So finally, we will get minus 1 over 11, 17 over 11, and so we can calculate the current for this loop and this loop. And then, of course, we, with these two current, with these two loop current, we can calculate the no voltage for here or there. So, for example, for this no voltage, it is something like for the no voltage here. For the no voltage here, we can calculate it as I1 minus I2 times R3. Nothing like that. So it's minus something minus 18 over 11 times 3, something like that. 16 over 11 times 3, so that we can calculate this is the V. Okay, so actually we can solve it like this. So for another way to solve this one is for the I remember this is called the mesh equation. This is called the node equation. The same value, I don't repeat it again. This is V1, V2, like this. So in this case, using the node equation is pretty tricky. We can call this one a supernode. So actually, if we regard it as a node and we apply the KCL, the Kirchhoff current law here, it is nothing but the current going outside of here, of here, of here. We sum that together, it will be nothing but 0. So first of all, we can assume this one is V, this one is V, this one is V. So for this current, maybe we can call it I1. I1 is nothing but V plus V1 over R1. So we can write V plus V1 over R1. This is the first term. And for the second term, this is I2. This is I2. So I2 is nothing but V over R3. And the third term, this is called I3 plus, so this is V plus V2, so we have V plus V2 over R2 equals 0. And we can solve V to be nothing but V1 over R1 plus V2 over R2, 1 over R1, 1 over R2, 1 over R3, something like that. And you substitute all the number in it, it's minus 34 over 11. So this is actually the same as this one. The same as this one. So this is what the student learned in the last semester. And maybe I can add something also interesting. They have something called the definite equivalent circuit. So it's something like a voltage source, which is called V series with a resistor R. This is called the definite equivalent circuit. They also have another called the Norton equivalent circuit. So it is nothing but a current source parallel with resistance. So these two circuits is equivalent with each other. The condition is that V equals IR. The R should be the same, and E and R should satisfy this condition. Then these two circuits is called the equivalent circuit. Equivalent means if you put it in a black box, you can test the voltage and current relationship. Then you cannot distinguish it whether it's this one and that one. If you cannot see what is inside the black box, and you can only give some voltage outside, you can vary the voltage and measure the corresponding current, then they will be the same. Of course, they will also learn the control source, but for other students, I don't think you really need to know about it. So I think this is more or less what they have learned for half a semester. And if you know these two methods, then you can go for half a semester in circuit analysis. When I was TA for circuit analysis 10 years ago, when I grading the exam, some of students may assume, every voltage and current and maybe tens of variables, and then they write tens of equations, and then they cannot, of course, they cannot solve it because they do not write it systematically, because you define the variable, which is really important, and then you write the same amount of equations, then you can solve them out. If you write redundant stuff, then usually if you can calculate correctly, you get 0 equals 0. Then you need to put whatever on it. So this is about the resistive circuit. So let's go back. Okay, let's come back here. So okay, it write a lot of equation. Okay, for here, it start to talk about the capacitance. So resistor and capacitance, in the sense of series and parallel, they are different. For series resistance, they add the resistance together. This is series resistance. But for capacitor, you add all the capacitance together. Then this is parallel capacitance. But for parallel resistance, this is the sum of inverse and take the inverse again. It is parallel resistance, and likewise for series capacitance. And a bit later, I'll let you know why it will be like this. So this is called the ampere meter and ammeter and voltage meter. Of course, a voltage meter is used to measure the voltage. So actually, the voltmeter or the voltage meter should be in a very large resistance, which means that if you connect the voltage meter there, the voltage meter shouldn't change the original circuit a lot, which means it shouldn't be much current going through this voltage meter. Otherwise, it would change the operation of the circuit. In other words, the voltage meter should have a very large resistance, or ideally, it should be infinite resistance so that no current will going through the voltage meter. And so that's for voltage meter. For ammeter, it is opposite. For ammeter, it is opposite. You try to measure. Originally, you don't have the ammeter. You want to know how much current going through this resistor, so that you series the ammeter with the resistor, so that you can measure this current. And contrary, the ammeter should have a very small intrinsic resistance, so that it doesn't really change the current going through this part, because originally the voltage across this part is fixed. So if you have a large resistance, then the current going through this part will be varied by the resistance of the ammeter. So this is ammeter and voltage meter. So let's come to the RC circuit. RC circuit is okay, it's pretty easy. And the only equation you need to know is I equals C dV dt. I equals C dV dt. You take the derivative of the voltage across a capacitor. This is the voltage across this capacitor, and this is the current going through it. So they will satisfy I equals C dV dt. How does it come from? Because you have Q equals CV. So you take the derivative on both sides. You take the derivative of both sides. So dQ dt is nothing but the current. And the right side will be C dV dt, because C is constant with respect to time, so you can factor it out. So you have I equals C dV dt. As long as you have this equation, you can calculate the circuit with capacitor. And this one is quite simple. So let me come back.
come back to here. Okay.
So, a RC circuit is something like this, not really the most fundamental RC circuit can be something like this. The R in series with a capacitor, and you have a voltage source here. So you have I equals dV dt, and so you have V, this part. So I will be this. So you write the loop equation, or the mesh equation. So this is I, I equals dV dt. So the voltage drop or the resistance is Ri, and so it is RC dV dt, and plus this is D, this is V. So simple. And for the right hand side, this is Vs, this is the source. So actually, you convert a circuit into a differential equation. So you can solve it in, you can solve the differential equation as you have learned it. Of course, for first order constant ODE is simple. You just substitute on the first derivative. You have S, the original function. So you substitute by 1 and equals 0. So you have N equals minus 1 over RC. So B is equal to E to the 1 over RC times T. So I suppose all of you are FST students, so you must have learned how to solve an ODE. This is a homogeneous solution, and of course there is a particular solution. It depends on what Vs is. If Vs is only a constant, so the particular solution is of course another constant. And you substitute this constant into the original equation. So dV dt for constant will be 0. So you have V over RC equals RC Vs. So V equals to Vs. However, there are different cases. For example, if Vs is something like a sine wave. So the particular solution would be something like E sine omega theta plus C cosine omega theta, omega t. And then you substitute into the original equation, and then you can find B and C. And with the initial condition, you can also find A. However, moreover, and you can have Vs equals to, for example, E to the A. A is another constant, so Vt is also another E to the AT, but something like that. Then you can also substitute it into the original equation, and then you can solve this constant. But what special case is that if A equals to minus 1 over RC, then Vt should be something like this. If this one repeated with this one, you need to multiply a t on
on the particular solution. And actually, when you learn how to solve the differential equation, you need to remember all these rules so that you can get the correct solution. But actually, these rules come from the Laplace transform. This rule comes from the Laplace transform. I think you have learned the Fourier transform. Fourier transform something like this. X of t natural to minus j omega t dt something like that. But the Laplace transform is similar. X of t e to the minus st dt. And when you learn the signal system in chapter 9, if I remember right, this also called a unilateral Laplace transform. So the definition is a bit different. It is something like this. Only half of it is considered. So you can use the Laplace transform. You can use the Laplace transform to solve it without memorizing all this rule. I suppose you have learned the Fourier transform so that you know. For example, if you have x of t, the Fourier transform pair is x of j omega. So if you take the derivative with respect to time for x of t, the Fourier transform pair would be something like j omega x j omega, something like this. I think you should know that. So for Laplace transform, it is quite similar. If we take the Laplace transform, it is nothing but something like this, which is the original Laplace transform. If you use the unilateral Laplace transform, it will be something like this. S x of s minus x of 0. So you have the initial condition here. So if you take the Laplace transform to this differential equation, if you take the Laplace transform to it, okay, move it up a bit. Okay. So we have this equation. If we take the Laplace transform on both sides, dv dt will have x of s minus x of 0 plus 1 over RC x of s plus 1 over RC Laplace transform of this guy. Laplace transform of this guy. I don't know what it is, but it depends on what it is. Laplace transform. So I move this term to the right side and we factor this out. So we have s plus 1 over RC. Something like this. Something like this. So you find that x of s, which is the Laplace transform of x of b of b, so you have something like this. X of 0 plus this one. So this is the homogeneous solution. This is how you change the first derivative to s and the original function to 1 so that you can get this term.
And actually, you know, for Laplace transform, you have exponential to at. This Fourier transform, you know that should be a plus j omega, 1 over a plus j omega. Right. Should be from 0. Should be minus the set function. Then I integrate from 0 to infinity. Then the Fourier transform will be something like this. Yeah. So likewise for Laplace transform, exponential to at ut, the Laplace transform will be something like this. So you know that the Laplace transform of this term, so you take the inverse Laplace transform, you will have x of t equals to x of 0 times exponential to minus 1 over r t. Something like this. This is the homogeneous solution. And of course, you can be part of the homogeneous solution. You still have this term. So if Vs is also maybe V0 times exponential to minus 1 over RCT, if Vs is something like this, so the Laplace transform of Vs will be nothing but is s plus 1 over RC. Yeah. So we substitute it here. This term will become RC 1 x 1 plus RC squared. So we have this Laplace transform or Fourier transform, and what you like. You don't like them either. So you have the square, and if you check the Fourier transform table or Laplace transform table, if you have something like this, it is nothing but t times the exponential to minus 1 over RCT, something like this. Because when you learn the Fourier transform, they have something like the duality. Because here we will have, for example, if x of t have a Fourier transform x of j omega. I just mentioned that x of t, and then you take the time derivative. What it is? J omega x j omega. So if you take the derivative on this side, it will something like you multiply t dt. Of course, there is something on the left side. I'm not really sure, but you can really check it. Because if you write this out, you have x of t exponential to minus j omega t, integrate from minus infinity to infinity. It is xj omega. So you take the derivative with respect to omega. You take the derivative on the left side also. So you can move this inside. You can move this inside. So you have x of t partial omega exponential to minus j omega t dt equals d omega x j omega. So you take the derivative with respect to omega, so you have minus jt minus jt is xt, and then you have the original one. Which means this one you will have minus j here.
Any questions?
So actually, if you like to solve the RC circuit in something like this, actually you substitute the first derivative to be s, or second derivative to be s squared, and original function as 1, and then you get the characteristic polynomial, and then you solve what is the characteristic value, and or the eigenvalue of this system. And you can write a homogeneous solution, and according to the right side, you can write a particular solution, and then you solve it with the simplest way to do that. And of course, you can use the Laplace transform to do that if Vs is the function. Or if you forgot the group, then you can follow the Laplace transform. So if Vs is only a constant, it is Vs, then so V will be Vs plus A exponential to minus T over RC if V0 is 0. If V0 is 0, then Vs plus A will be 0. So A will be minus Vs, then we will get V of T will be V1 minus exponential to minus T, something like this. This is what we can on the textbook. Okay, so this is the RC circuit. Okay. So this is the second order equation.
well, or second order circuit, something like that. This is the LC. This is the energy stored in the electric field and magnetic field. And here it mentioned the LC oscillation circuit. LC oscillation circuit. It is nothing but it is assumed like this. You have a inductor and capacitor, something like that, and you try to, for example, you have a source. You try to store some energy inside, and then you disconnect it sometimes later, then it will keep oscillating. If there are no internal resistance, then it will oscillate forever, something like the simple harmonic motion. Because it is very simple, it's something like F equals ma, something like F equals ma. You're familiar with F equals ma, which is mx double dot, and the Hooke's law is something like kx minus kx. So you have a second order plus kx equals 0. You have a second order differential equation. And likewise for this one, for the voltage, we can write V. So the current going through the capacitor is nothing but I equals C dV dt. So if you connect it, if you disconnect it later on, it is something like the L is both series and parallel with the capacitor. So for the inductor, it is nothing but L di dt equals V for the inductor. So if I is going this way, I is also going this way. So you can substitute this into here. So you have LC V double dot plus V equals 0, something like this, which is quite similar to that. If you're familiar with the spring oscillation, then you can get the idea of it. And of course, the omega is 1 over square root of LC, because it is second derivative with respect to the time. So you substitute it to be s squared, substitute v to be 1, so LC s squared, LC s squared plus 1 equals 0, so that you get two complex roots, complex conjugate root. And of course, the answer is a sine or cosine function. So you write it like this. And okay. Okay, so let's come back to here. So for RLC circuit, L, C, D, this is BL plus minus BR plus minus
So we'll get I equals C dV dt, of course, and ER is nothing but IR, so it is RC dV dt. EL is L dt, so it is LC D 2 D dt squared, something like this. And then we write the loop equation, so we have LC V double dot plus RC V dot plus V equals Vs. We have a second equation, second order ODE like this, and of course, or you can normalize it like this: R over L V dot plus 1 over L C equals Vs over something like this. So there are three cases. So delta equals E square minus 4AC. E square minus 4AC. Okay. So which is R square L square minus 4LC. So there are three cases. You should have learned it in the high school. If delta is larger than 0, so there will be two loop roots. If delta equals to 0, repeated loop roots. If delta is smaller than 0, complex conjugate root. Complex conjugate roots. So this is something like if the two poles are S1 and S2, yeah. So it will be something like A exponential to S1t plus B exponential to S2t. This is the homogeneous solution. For this one, this will be something like A plus B times T exponential to S. S1 and S2 are the same, so I can write either one of them. But if it is a complex conjugate, if it is alpha plus or minus J beta, one point I forgot to mention. We usually write square root of 1 to be J rather than I. So for complex conjugate root, the solution will be something like A exponential alpha T, sorry, it should be something like this, cosine beta T plus E sine beta T. Should be something like this, and then you determine the A and B. So it's still a ODE problem. Still an ODE problem. Okay. So for three-phase. Okay, so this is the phasor. Okay, so we have three phasor. One is XC equals 1 over omega d Z, or we would usually write it as ZZ equals to 1 over J omega C. Write it as a complex number. And for resistance, it of course this is an inductor, so we'll write it as ZL CL equals to J omega L. This is what we know as the phasor. And of course, this is something similar to the
the simple Ohm's law, V, or you can write it as ZR equals to R. It's nothing but a real number. So why the phasor will look like this? Why the phasor will look like this? Anyone can tell me? It is because the Fourier transform. Because for this one you have like, so this is nothing special for L, because you have VL equals L di L dt. So you take the Fourier transform on both sides, you have VL equals L. So time derivative. So take the Fourier transform, it will become J omega and IL. So we define ZL something like the VL over IL. Then it will become J omega L. And likewise for the capacitor, you have IC equals C dic dt. So you take the Fourier transform on both sides. So you have IC equals C. This is time derivative. So it becomes J omega R V. This is V. So you have VC. So you also define this is VC over IC. Then it will become 1 over J omega C. So this is because we have a Fourier transform. So the phasor is defined like this. And with the phasor, you can calculate the RLC circuit more simple. But using this method, you cannot calculate the homogeneous solution or the transient response. You can only care about the steady state response, because usually for the second order equation, if it is stable, which means that this term will have a negative coefficient for the exponential function. So it usually decay, and it will diminish. So after a long time, it will diminish. So only the steady state response will still be there. And phasor is a way to calculate the steady state response. You can just simply change the RLC into the phasor, and then you calculate it usually, and then you transform the sine wave with the frequency to be its corresponding phasor, and then you calculate assuming it is like a resistive circuit, and then you calculate out, and then you get a complex number, and then you convert it back to a sine wave. But if you ask, if we have multiple frequency for this circuit, then you can use a superposition. You can calculate for frequency 1 and frequency 2 independently, and then you add them together. So that because the phasor depends on the frequency, omega is 2 pi f. Omega is 2 pi f, which is related to the frequency. So with multiple frequency, you need to separate them, and then you calculate one by one. But if you ask, we have many frequency for the source, how come it will be? You use the Fourier transform. You can transform it from time domain to frequency domains. Then you can distinguish different frequency of the original signal, and then you multiply by the transfer function of the circuit, and then you get the output. Because you have it's something like you have a x of t, you convolve with the impulse response of the circuit. So you will get the output. So if you take the Fourier transform, it is nothing but yj omega equals xj omega times hj omega. So hj omega is only related to the circuit itself, and xj omega is only related to the input signal. So you get the output signal, something like this. You only need to calculate the Fourier transform of them, multiply them together, and then you get the Fourier transform of the output signal, and then you take the inverse Fourier transform, then you can get the output signal in time domain. You don't really need to calculate the convolution. So I think, yeah, you will calculate something like that. But how does it come from? Okay, you feel like you convert it R to R. This is 1 omega C. This is J omega L. Then you sum of them together. This is the real part. This is the imaginary part, and then this is the amplitude. So you take the square and add them together and take the square root. So this is the amplitude for the impedance. So this is the impedance, and if it's something like this. And this is a root mean square. Root mean square means you take the square of it and then take the average and take the square root. So for a sine wave, it is nothing but dividing by square root of 2. You can just calculate the integration easily using the double equation, for the double angle equation. And this is the transformer. So it will amplify the voltage, but so this term NS over NP, NS over NP, but here NP over NS. So that, which means that the power at the primary term and the secondary term are the same. So that for voltage you multiply by this term, but for current you divide by the same term. So it's the reverse. So equivalently, the equivalent resistance is multiplied by the turn ratio square. So if you see R here, in here you see the turn ratio square times R will be the resistance you see at the primary turn.